The AC generator is one of the cornerstones that make modern technology possible. Just about every household appliance or industrial system is ultimately being powered by a generator, and that generator is most likely to be an AC generator. So it is important for us to understand how something that is so basic to the modern world works. So let's delve into the most simplified design that is imaginable for an alternating current or AC generator. Here we have a schematic. An AC generator requires a magnetic field to operate. This field needs to be uniform in distribution. This is accomplished by using the opposite poles of a magnet kept at a calculated distance from each other. Next, we come to the coil. Now, the EMF and current are induced in this rectangular coil. Now, for simplicity, we will assume operation using just a single rectangular coil to make our calculations and understanding easier. In this case, we have two longer arms of this coil across which the EMF is going to be induced. Here, the entire arrangement is being rotated along an axis, and that axis is decided by the axle. It is this axle which is connected to some source of mechanical energy. Now, the voltage and current are conveyed from the rotating ends of the coil through these structures which are called slip rings. So, whatever EMF and current is induced is picked up using these slip rings. The slip rings are in turn connected to carbon brushes. These carbon brushes are made from soft graphite, which is slippery as well as conducting. So as the entire arrangement rotates, the carbon brushes will remain fixed in place and they will conduct away the voltage and the current away from this device. Now, there is a change in the magnitude and in the direction of voltage. Let us understand how. So why is the voltage alternating? We know that the coil is being rotated using an external source of energy. It can be a turbine, it can be a windmill, it can be a mechanical generator, it can be any system that is rotating and is linked with the coil. The rotation of the coil changes the angle of the plane of the loop with respect to the uniform magnetic field. So let's start our analysis. So here we have the beginning state. The arms PQ and RS are oriented perpendicular to the magnetic field. In other words, the plane of this coil is perpendicular to the direction of the magnetic field. Now, in this case, the coil has rotated by 90 degrees, which corresponds to 1/4 or 25% of a full cycle. A full cycle is one complete rotation of the coil. Now, again, we have rotated by another 90 degrees. So, from the beginning, we have gone through 180 degrees of rotation. So, PQ and RS are now on opposite sides as they were before. Now, the coil has gone through a rotation of 270 degrees. This is the same orientation as stage 2, but the arms are in the opposite positions to stage 2. And finally, the coil completes one entire rotation and the arms SR and PQ come back to their original states. So what we are seeing is that the coil is continuously rotating in the presence of this magnetic field, and the relative positions of SR and PQ are changing with respect to the axis of the magnetic field. And this gives us a clue as to why we are getting a variable voltage coming out of this device. So let's try to understand this mathematically. We know that at any given time t, the coil is cutting through a specific amount of magnetic flux. So at time t, the magnetic flux that is linked with the coil is given as phi b is equal to b times capital A cos theta. Here b is the field of the external magnet, A is the cross-sectional area of the coil, and cosine theta is the angle formed between the area vector of this coil and the external field. So we can replace theta with omega t, where omega is the angular frequency. So we have phi b is equal to capital B times capital A times cos omega t. Now, we know that from Faraday's law, the variation of the flux with time multiplied by the number of turns gives us the EMF, and this EMF has a negative polarity, meaning it is always opposing its cause. So from that we get that E, that is EMF, is equal to negative d phi by dt, that is equal to negative n times capital B times capital A d cos omega t by t. So taking this derivative, we get the new result, that is the instantaneous EMF generated in the coil at any given time t, and that is E is equal to negative capital N times capital B times capital A omega sine omega t. Here capital N is the number of turns in the coil. So we understand that at any given time, the angle that is being made between the area vector and the external field B is giving us the EMF. We also know that the value of the sine function is maximized at the angle 90 degrees. So here we see that the peak EMF in this system, in this generator, is reached when the angle between the area vector of the coil and the external field is 90 degrees. For 0 and 180 degrees, that is, at the beginning of the rotation and halfway through the rotation, we have 0 EMF because sine 180 and sine 0 are equal to 0. And then again, we reach the negative peak value at 270 degrees because sine 270 is negative 1. And again, when we come back to the original point, that is 360 degrees, the beginning of the rotation, again the value of EMF becomes 0. So putting it all together, we can see how different orientations of the coil are corresponding to different EMFs inside the system. We can see that the EMF reaches its peak value for theta is equal to 90 degrees. That is when the coil has rotated through 1/4 of the rotation and it increases in the negative direction to a negative maximum value at theta is equal to 270 degrees. So we see that for a given rotation of the coil, the output voltage is increasing to a max positive value, going back to 0 and then going to a max negative value and increasing back to 0. This is what we call alternation. So let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.